Hi, everyone, and thanks for joining me today. I'm Alan Yang from Stanford University, and I'm excited to share our recent work on designing spreading codes for satellite navigation using mixed integer optimization. This is joint work with Taramina and Grayscale. Spreading codes are binary sequences that allow receivers to acquire signals, maintain precise timing, and suppress interference. Traditionally, codes such as the gold codes and wheel codes are used. They have a low auto and cross correlation and can be generated on the fly without needing to be stored in memory. However, there are only a few such known codes, and they tend to only be available for certain code lengths. Here, we aim to design new codes for modern receivers, which can easily store large code families directly in memory. In this work, we show that the problem of finding binary sequences with low autocorrelation and cross-correlation can be formulated as a mixed integer program, essentially a convex optimization problem with binary variables. If we ignore the binary constraints, the problem would be convex and efficiently solvable. For very small problem instances, a specialized solver such as Gurobi can actually be used to find globally optimal codes. In practice, since solving the full problem exactly is still intractable for codes with thousands or more entries, we use a block coordinate descent method. At each iteration, we fix most of the code entries and optimize only over a small subset of, say, 15 of the code entries. In practice, we find that a solver like Gurobi can solve these subproblems much more quickly than can be done through brute force enumeration. We found that our method outperformed gold codes and a natural evolution strategy, or NES, after just a few hundred iterations. We also explored different choices of objective function that assign different weighting to autocorrelation and cross-correlation values, as well as balance constraints to keep the number of positive and negative entries in each code to be equal or at least nearly equal. Because our approach requires almost no tuning to work well, designers can devote their effort to defining and exploring different objectives and constraints rather than on performing the optimization itself. For example, we may focus on minimizing peak side lobes or enforcing zero autocorrelation at one chip shifts. Notably, the Air Force Research Lab's upcoming NTS-3 mission, which is equipped with reprogrammable transmitters, can provide a great testbed for evaluating new codes and objective functions as well as constraints. Thanks for your interest in our work.